Okay, in this lecture we're going to cover the first part of our section 13.6 material on applications of integrals. So one application that we're going to focus on throughout this section is the following. If a function gives the rate of change of some quantity, so the derivative of some quantity, then the area between the graph of that rate function and the x-axis, which we know is given by a definite integral, is the total amount of that quantity. So we're going to consider some applications of this throughout this section. So let's start with the following example. We have a car leasing firm which must decide how much to charge for maintenance on the cars it leases. So after some study, the firm determines that the rate of maintenance, which is given by m of x, so this is the rate of maintenance, or the derivative of maintenance, on a new car will approximate the function m of x, which is 60 times 1 plus x squared dollars per year, where x is the number of years the car has been in use. So given this information in part A, we're asked to find the total maintenance cost during the first 3 years. So in order to find this total maintenance cost in the first 3 years, we could look at the integral of our rate function, which was 60 times 1 plus x squared. And we would integrate this with respect to x over what x interval? Well, we were asked about the total maintenance for the first 3 years. So we would start with the beginning of the first year, which would correspond to x equals 0. 0 years have passed, up through 3 years passing. So let's see if we could evaluate this integral. So my first step, I might simplify a little bit by distributing the 60. So I would have a 60 plus 60 times x squared, and we're integrating from 0 to 3. So the fundamental theorem of calculus says we just need to find an antiderivative of this function. So the antiderivative for 60 would be 60x plus the antiderivative of 60x squared would be 20x cubed. And then we evaluate this antiderivative from 0 to 3. So substituting our upper limit of integration, 3, in for x, we have a 60 times 3 is 180. Plus 20 times 3 cubed, which would be 27, gives us 540. And then the sum of these values is 720. And here our rate for maintenance was measured in dollars per year, so this amount would be measured in dollars. Now in part B, we're asked what minimum amount should be added to the monthly lease payments to pay for maintenance on a 3-year lease. So this company charges some monthly rate to lease vehicles. Let's say that someone is getting a 3-year lease. What additional monthly charge should be added in order to account for this expected maintenance over a 3-year period? So here, using our result from part A, we can say the maintenance cost for a 3-year period is $720. So if we're talking about a monthly charge, well, our 3-year period would be 36 months, since there's 12 months to a year. So the minimum monthly payment should be our $720 divided equally among 36 months, which would give us a rate of $20 per month. So that would be the additional charge that would be needed to account for the maintenance on a vehicle over a 3-year lease. So let's look at another example. In this next one, we're told a company is introducing a new product and production is expected to grow slowly because of difficulties in the startup process. So it is expected that the rate of production will be approximated by the function p of x is equal to 1,000 e to the 2x, where x is the number of years since the introduction of this product. So here we're given a function p of x, which is the rate of production, or rate of change of the number of units being produced. So in part A, we are asked to find the total number of units that this company can supply during its first 2 years. So since we have this rate function for production, p of x, the total number of units that they can supply in the first 2 years is given by the integral of this rate function over what x interval? Well, the first 2 years would correspond to an interval from 0 to 2. So, to evaluate this integral, we would make use of the fundamental theorem of calculus. So to start, we could maybe move our constant 1,000 out in front of this integral, and we're left with the integral of e to the 2x from 0 to 2. So we have our constant 1,000, and the antiderivative of e to the 2x is 1/2 e to the 2x, which we then evaluate from 0 to 2. So, simplifying a little bit, we have a 1,000 times 1/2, which gives us 500 e to the 2x, evaluating from 0 to 2. So I have my constant 500 out in front, and then I evaluate this antiderivative when I substitute 2 in for x, so that would give me e to the 4th. And then I subtract the value I get by substituting x equals 0 into the antiderivative, which would be e to the 0, which is 1. So using a calculator to approximate this value, 500 times e to the 4th minus 1 is approximately 26,799 units. So just shy of 27,000 units can be produced during the first 2 years. So then in part B, we're asked, given this information, will the company be able to supply 50,000 units during the first 4 years? Before we answer that question, let's think about this intuitively. We have shown in part A that in the first 2 years, the company can produce 26,000 or about 27,000 units. So if we ask about 50,000 units, which is a little less than double of our 27,000, could that be produced during the first 4 years? So if we were to double the timeline that we have. So we would expect that, yes, this should be possible, especially since our rate of production is given by p of x, which was an increasing function. It's increasing exponentially. So intuitively, we would expect that, yes, this is possible, but let's verify. So To determine the total number of units the company can supply in the first 4 years, we would integrate our rate function, which was 1,000 e to the 2x dx, from 0 to 4. Now in part A, we showed that the antiderivative of this function was 500 e to the 2x, and then we will evaluate from 0 to 4. So we have our constant 500 times, when we evaluate at x equals 4, we have e to the 8th, minus the value when we evaluate at x equals 0, which would be e to the 0, or 1. So again, using a calculator to approximate this value, we find that this is approximately 1,489,979 units, which is certainly greater than the 50,000 that are asked about here. So we could say definitely we can supply at least 50,000 units within the first 4 years. So in the next part of this section, we'll talk about determining the area between two curves, and then we'll talk about some applications of finding the area between two curves if we have rate functions for two quantities that may be related somehow. So I mentioned here that in some applications, it is necessary to find the area between two curves. So for instance, just to illustrate the idea, consider the region between the graphs of two functions, say y equals f of x and y equals g of x on the interval from a to b. So here, suppose that we have maybe just in the first quadrant of the xy plane, the graphs of two functions. Let's say y is f of x and some other curve, which is the graph of a function y equals g of x. And we consider the region between these curves on the x interval from a to b. So let's say that I want the area of this shaded region that lies between those two curves. Now we know that the definite integral of a function over some interval gives the area underneath that curve and above the x-axis. So if I were to consider the area of the entire region under the graph of f of x, which would be the integral from a to b of f of x dx, this would be the area under the curve y equals f of x. And if I were to then consider just the area under the graph of g of x, that would be given by the definite integral of g of x over our interval. So to find the area between these two, well, I could take the total area under the graph of f of x, and if I were to subtract the area under the graph of g of x, then I'm just left with the shaded area that I was interested in. So to get the area between these curves, let's call that A, I would take the area under the larger curve and subtract the area under the smaller curve. However, by properties of definite integrals, if I'm evaluating the integral of a difference of two functions, that is the same as the integral of the difference of those two functions, f of x minus g of x. So we have the following result for finding the area between two curves. So making this a little more formal, if f and g are continuous functions, and f of x is greater than or equal to g of x on the interval from a to b, then the area between the graphs of f of x and g of x on that interval is given by the definite integral of f of x minus g of x. And we've got to be a little careful about our difference here. So we're taking the upper curve, f of x, and then subtracting the lower curve, g of x. So we want to make sure that we don't have that value backwards. So looking at an example of this, we're asked to find the area of the region between the curves y equals x squared and y equals 8 minus 2x on the interval from 0 to 3. And as a hint here, we're told to check to see whether these curves intersect on the given interval. So in some problems, we might have two curves which cross each other within our interval of interest, and then the same curve isn't always the top curve, as we've illustrated it in our picture here. So to check whether these two curves intersect within our interval, we would set the values of these functions equal to each other. That is, x squared would be equal to 8 minus 2x. So to solve for x, we could move everything to one side of our equation, say the left-hand side, and we would have x squared plus 2x minus 8 is equal to 0. And then this can be factored as x plus 4 times x minus 2 is 0. So our values for x are negative 4 or positive 2. So we see that one of the points of intersection, namely when x is 2, lies within our interval of interest from 0 to 3. So we need to determine on what part of this interval f of x is the top curve and on what interval g of x is the top curve. So to illustrate this, let's make a rough sketch for our functions here. So here we're looking at the curves y equals x squared, which is a parabola opening upward with its vertex at the origin. And then we have the curve y equals 8 minus 2x, which is a line whose y-intercept is 8 when x is 0, and it has a slope of negative 2. So it looks something like this. And we see that this point of intersection was when x equals to 2. And we're looking at this over the interval from 0 to 3. So not drawn to scale here, but we've got our illustration. So we're looking, let me maybe use some different colors. So I'll use a red line to denote my one curve, which is 8 minus 2x, and then I'll use a blue curve for the graph of y equals x squared. And we see that on the first part of our interval, from x equals 0 up to 2, the top curve is our line, 8 minus 2x, and the bottom curve is x squared. And on the remainder of our interval, from 2 up to 3, we have the blue curve is on top and our red curve is on bottom. So to find the area between these two curves, we would find the area of our first region, that is from 0 to 2, where the top curve is the line, 8 minus 2x. So to get the area between those two curves, we would take the equation of our top curve, 8 minus 2x, and subtract the equation for our bottom curve, x squared. So this piece is giving us the area of this region from 0 to 2, where our top curve is the red curve and our bottom curve is the blue one. Now, we add to that the integral from 2 to 3. We have the top curve on this interval would be our blue curve, which is x squared, and then we are subtracting the bottom curve, which is our line, 8 minus 2x on that interval. So this expression gives us the area of this small region where x squared lies above our line. Okay, so let's evaluate each of these integrals. So simplifying a little bit, we have for our first piece 0 to 2, 8 minus 2x minus x squared dx. For our second piece, integral from 2 to 3 of x squared, we were subtracting a negative 2x, so we have plus 2x and then minus the constant 8. So finding an antiderivative, we have 8x minus 1x squared minus 1/3 x cubed, which we evaluate from 0 to 2. And then we add a 1/3 x cubed plus 1x squared minus 8x, evaluated from 2 to 3. So for the first integral, we have, when we evaluated x equals 2, we have 8 times 2 is 16, minus 2 squared is 4, minus 2 cubed, which is 8 times 1/3, gives us 8/3. Then we subtract what we get when we evaluate at x equals 0, which is 0 in this case. Then we add, for our second integral, when we evaluate at x equals 3, we would have 9 plus 9 minus 24. And then we subtract what we get when we evaluate at x equals 2, which would be 8/3 plus 4 minus 16. So after some simplification, we are left with 38 over 3 for the area between those two curves over the given interval. So this example illustrating that if we have two curves which intersect somewhere within our interval, we might have to evaluate the region or the area of the region between those curves by splitting this up into two parts, depending on which curve is the top curve over a given interval. So let's consider some applications of finding the area between two curves. So in this next problem, we're told that a new smog control device will reduce the output of sulfur oxides from automotive exhausts. So if it is estimated that the rate of savings in millions of dollars per year to the community from the use of this device in a given year X will be approximated by S prime of X, which is negative x squared plus 4x plus 8. So here we're told that the rate of savings measured in millions of dollars per year is given by this derivative of the savings function, S prime of X. So the total savings, as we saw in our first couple of examples, would be the integral of this rate function over some x interval. Now, we're also told this new device cuts down on the production of sulfur oxides, but it causes an increase in the production of nitrous oxides. So the rate of costs in millions of dollars per year, so here we have a rate for a cost function, also measured in millions per year, to the community in year X is approximated by the derivative C prime of X, which is 3 over 25 X squared. So given this information in part A, we are asked, well, to maximize the net savings, for how many years should the new device be used? So let's consider how we would determine the timeline to maximize our net savings. So here I'll say the maximum savings will occur when the rate of savings is equal to the rate of cost. So let's think about why that would be the case here. So the easiest way, I think, to explain this is to consider the graphs of these two rate functions. So here, let's consider the graphs of these. So our rate function for savings is a quadratic, which has a negative x squared coefficient, so it's a parabola opening downward. And we see that when x is equal to 0, the y value would be 8. So we have some parabola opening downward, looking something like this, is our s prime of x, a rate function for savings. Whereas our rate for costs, c prime of x, is 3 over 25 x squared, which is a parabola opening upward when x is 0, y is 0, and then this parabola opens upward. So we see that the savings, or the savings rate of savings would be greater than the rate of costs up until this point of intersection, when the costs start to exceed the rate of savings. So in order to maximize our savings, we would only want to use this machine over, or this device over an interval from x equals 0 up until whatever year of intersection we have. So to determine that time, we would set these two rate functions equal to one another. That is, 3 over 25 x squared would be equal to negative x squared plus 4x plus 8. So to solve for x, we could move all of our expressions to one side of the equation, maybe the left-hand side. So if I were to add 1 x squared to both sides, I have 3 over 25 plus 1, which is 25 over 25, so 28 over 25 x squared. Then I would subtract 4x and 8 from both sides, and I have the following equation. Now what I don't like here is the fraction for my x squared coefficient. So if I multiply everything through by 25, I have 28x squared minus 4 times 25 is 100x, minus 8 times 25 is 200, equals to 0. And then if I divide everything through by 4, I have 7x squared minus 25x minus 50 is equal to 0. So this quadratic can then be factored as 7x plus 10 times x minus 5 is equal to 0. So we have for our x values either negative 10 over 7 or positive 5. So if x is equal to, we can't have x being a negative value here, since x is the number of years since the introduction of this device. We would have only the positive value, x equals 5 years. So here, in order to maximize the net savings, where the rate of savings is greater than the rate of costs, we would look at a timeline of 5 years. Now in part B, we're asked what will the net savings be for the period found in part A. So what are the actual net savings? So here I'll mention the actual savings. So that is the net savings are the difference between the savings and the total additional costs. Okay, so our net savings could be calculated as the difference between the total savings over the period for which we use this new device and the total costs over the period which we use this additional device. So the area under the graph of our rate function for savings, shown here, would give the total savings, whereas the area under the graph of our cost function would give the total costs over that interval. So the difference in those values is then the area between those two curves over our interval for which we're using this device. So to find the area between those curves, we would integrate over the time interval from 0 to 5. The upper curve, which is our rate of savings, which is negative x squared plus 4x plus 8, minus the lower curve, which was 3 over 25x squared. So let's see what we have. Simplifying our integrand, we have the integral from 0 to 5 of a negative 3 over 20, negative 1, and then minus 3 over 25 gives us negative 28 over 25 x squared plus 4x plus 8 dx. So integrating, we have a negative 28 over 25 times 3, which is 75 x cubed, plus 2x squared plus 8x, which we are evaluating from 0 to 5. So evaluating at x equals 5, we have negative 28 over 75 times 5 cubed, which is 125, plus 2 times 5 squared gives us 50, plus 8 times 5 is 40, and then we subtract the value that we get when we evaluate at x equals 0, but we see that that would be 0. So we're left with 90 minus 28 times 125 over 75. After a little simplification, this gives us 130 over 3. or approximately 43.3. So here, since these rate functions were given in millions of dollars per year, this 43.3 is measured in millions of dollars. So the net savings are approximately 43 million, if we round to the nearest $1 million. Okay. So let's look at another example. So in this next problem, we're told that the rate of expenditure in dollars per year for maintenance of a certain machine is given by m of x is x squared plus 6x, where x is time in years, and the machine produces a rate of savings in dollars per year given by s of x is 360 minus 2x squared. So in part A, we are asked how many years, or in how many years will the maintenance rate equal the savings rate? So to determine when those rates are equal, we would set these two functions, x squared plus 6x and 360 minus 2x squared, equal to one another. And moving everything to one side of our equation, say the left-hand side, well, if we add 2x squared to both sides, we have 3x squared plus 6x, and then if we subtract 360 from both sides, we're left with the following. So we see here that everything is divisible by 3. So if we divide through this equation by 3, we have x squared plus 2x minus 120 is equal to 0. And this can be factored as x plus 12 times x minus 10 is 0. So x is either negative 12 or 10. But here, since x is time measured in years, it can't be negative. So we would say after the only positive value, which was x equals 10 years, the maintenance rate would be equal to the savings rate. So in part B, to determine the net change over this period, as in our last example, we would consider the total expenditure, the total rate of savings minus the total expenditure to get the total or net change over this period. So we know that the total savings would be the integral over our time period from 0 to 10 of the savings function, which was 360 minus 2x squared. And then we subtract the total expenditure, which would be the definite integral from 0 to 10 of our expenditure rate function, which was x squared plus 6x. So this amounts to finding the area between those two curves. So let's see what we have. Simplifying a little, we have the integral from 0 to 10 of 360 minus 6x minus 3x squared dx. And so finding an antiderivative, we have 360x minus 3x squared minus 1x cubed on the interval from 0 to 10. So evaluating this antiderivative at x equals 10, we have 360 times 10, which would be 3,600, minus 3 times 10 squared is 300, minus 10 cubed, which would be 1,000, and then we subtract the value that we get by evaluating at x equals 0, which is 0 here. So we're left with 3,600 minus 1,300, which gives us 2,300, measured in dollars here. Okay. So in the next part of our section, we'll talk about some other applications of integration. And the first one is determining the present value of some future income stream. So you might recall from your business mathematics class, not business calculus, but business math, that the future value, let's call it FV, of some present amount of money, let's call it a present value, if it's compounded continuously at a rate of R% per year, would be given by the present value times e to the R times t, where t is the number of years that this present amount is left to gain interest before we make a withdrawal for our future value. So using this equation, we can say if we have a sum of money that can be deposited today to yield some larger future amount, we would call this the present value of that future amount. So solving this equation for the present value, we would take the future value and divide by e to the RT. So that is the present value, PV, of a future value, FV dollars, at an interest rate of R per year, compounded continuously for T years, is P of E, which is FV over e to the RT, or equivalently FV times e to the negative RT. Now let's change this problem slightly. Let's suppose that instead of a single future payment of FV dollars, we want a future income stream at a rate of FV of T dollars per year over the next T years. So instead of a single withdrawal at some future time, we're making a series of withdrawals to have some income stream which varies over time. So it's a function of time measured in dollars per year for a period of capital T years. So in this case, the present value, PV, of that future amount that we must deposit today in order to secure that income stream is given by PV, and it would be the integral of our income stream function times e to the negative RT over the interval from 0 to capital T, where capital T is the number of years that we would like to have this income stream. So let's look at an example of this. Here we are told to assume an interest rate of 2.5% per year, compounded continuously, and find the present value in each of the following situations. So in part A, find the present value of a single future payment of $10,000 20 years from today. So here we're looking at a single future payment. So to find the present value for that single future payment, we would take the future value and multiply by e to the negative RT, the same formula that we had above in the event that we're making a single, or we're looking at a single future payment. So here our present value is given by the future value, which was 10,000 times e to the negative R. So here our interest rate was 2.5%, which as a decimal is 0.025 times t, and the number of years that we're passing before we make that withdrawal was 20. So making use of a calculator to approximate this value, we have approximately $6,065.31 if we round to the nearest cent. Now in part B, we're changing this problem slightly. We're asked what is the initial deposit required to fund a future income stream of $10,000 per year over the next 20 years. So here we're looking at the income stream problem. The present value required to sustain that income stream is the integral over the timeline of this income stream. So for a period of 20 years, we would have year 0, or right now, up through 20 years from now. And we're integrating our income stream, which would be a constant $10,000 per year over time, times e to the negative RT, where R is, as a decimal, 0.025 t, and then we're integrating this with respect to t. So for simplicity, we can pull the constant 10,000 out in front. We have the integral from 0 to 20 of e to the negative 0.025 t dt. So we have 10,000 times our antiderivative would be 1 over negative 0.025 times e to the negative 0.025 t, which is then evaluated from 0 to 20. So recall, we're using the fact that the antiderivative of e to some constant times x with respect to x is 1 over that constant times e to the same power. So in this example, our constant k is just this negative 0.025. So simplifying a little bit, taking that 10,000 and dividing by negative 0.025, we have negative 400,000 times e to the negative 0.025 t, evaluating from 0 to 20. So when we evaluate at 20, we have e to the negative 0.025 times 20, minus, when we evaluate at 0, we have e to the 0, or 1. And using a calculator to approximate this value, we are left with 157,387.74 if we round to the nearest cent. All right. So in the last part of this section, we'll talk about a concept known as consumers or producers surplus. So as we've discussed in our previous section, the market will determine the price at which a product is sold. In particular, the point of intersection of the demand curve and the supply curve for a product gives what's called the equilibrium price. And at this equilibrium price, consumers will purchase the same amount of the product that the manufacturers are willing to sell. However, some consumers are willing to spend more for an item than the equilibrium price. So if we consider the total of the differences between the equilibrium price for this item and the higher prices for all individuals who are willing to pay. This is what's called consumer's surplus. So to illustrate this, let's look at a figure. So in the figure below, the total area under the demand curve from Q equals 0 to Q equals Q naught is the total amount of consumers willing to spend, or the total amount that the consumers are willing to spend for that equilibrium amount Q naught items. So here we have some demand curve shown in red, and we have a supply curve shown in blue, and the point at which those two curves intersect is our equilibrium point. So the quantity is what we call Q naught, and the corresponding price is what we call P naught. It's our equilibrium quantity and equilibrium price. So here, if we're considering the total area under this demand curve from Q equals 0, so starting from 0 quantity up through Q equals Q naught, so this total area, we would have the total amount consumers are willing to spend for this Q naught number of items. Now, if we consider the area under the line y equals P naught on that same interval, this would show the total amount consumers will actually spend at this equilibrium price of P naught. So if we consider the constant value y equals P naught and integrate over 0 to Q naught, we have the following shaded area. Now, the area between those two curves, so if we take the difference of those two areas, that amount represents the consumer's surplus. So if we take the area that I had first shaded and subtract the area of this black rectangular section, what I am left with is some region shown here. And this region is what we are calling the consumer surplus. It's the area of the red region shown in this original figure. Okay. Now, if we're talking about something called producer surplus, if some manufacturers are willing to supply this product at a price lower than the equilibrium price, P naught, then the total of the differences between the equilibrium price and the lower prices at which these manufacturers would sell the product is called the producer surplus. So in the figure that we've shown below, if we consider the total area under the supply curve, so that was the curve shown in blue, from Q equals 0 up through Q equals Q naught, so that is this area. This would be the minimum total amount the manufacturers are willing to realize from the sale of Q naught items. Now, if we consider the area under the line y equals P naught, so this constant value on the same interval from Q equals 0 to Q equals Q naught, that is this shaded region, that value shows the amount actually realized by the manufacturers at the equilibrium price of P naught. So the area between those two curves represents the producer's surplus. So if I take the difference of those two values, those two areas, I'm left with this region shown in blue. The area of that region is producer's surplus. So let's think about how we find those areas. So here we get a formula for consumers or producer surplus. Now we know to find the area between two curves, we're just integrating the difference of the functions which describe those two curves. So if we have a function d of q, which is a demand function, which has an equilibrium price p naught and an equilibrium demand q naught, then the consumer surplus is the area under the graph of the demand function d of q minus the area under the curve which defines our equilibrium price p naught over the interval from 0 to the equilibrium quantity, Q naught. And similarly, the producer surplus can be found by looking at a supply function, S of Q, which has an equilibrium price of P naught and an equilibrium supply of Q naught. This would be the area under the line defined by the equilibrium price, P naught, minus the area under the demand function, or the supply function, over our interval from 0 to Q naught, the equilibrium quantity. So let's look at an example of finding producers or consumer surplus. So here let's suppose that we have the supply function of a certain item given by S of Q and the demand function for some item given by D of Q. We're asked to find the point at which the supply and demand function are in equilibrium. So to find that point, we would let our supply, which is Q squared plus 10Q, equal the demand function, 900 minus 20Q minus Q squared. And so to solve for Q, if we move everything to one side of our equation, let's say the left-hand side, we would have 2Q squared plus 30Q minus 900 is 0. And then I can divide this equation through by 2. I have 1Q squared plus 15Q minus 450 is equal to 0. And this quadratic can then be factored as Q plus 30 times Q minus 15 is 0. So we find that either Q is negative 30 or positive 15. It doesn't make sense for a quantity to be negative. So if our quantity demanded is 15, we still need the price to find the equilibrium point. So let's say if Q equals 15, then to get the corresponding price, let's denote these as Q naught and P naught for equilibrium values, we would have our function, either supply or demand. I'm going to take the supply function S, and I would evaluate at 15. So here I have 15 squared, which would be 225, plus 10 times 15 is 150. So that would give me 375. If we're measuring in dollars, it'd be $375, and the quantity demanded would be 15 units. And now in part B, we are asked to find the consumer surplus and producer surplus. So let's start with the consumer's surplus. So we said we would integrate over the interval from 0 to, in this case, 15, our equilibrium quantity. The difference in the demand function, which is 900 minus 20q minus q squared, minus the equilibrium price, which was 375, integrating with respect to q. So simplifying a little, we have the integral from 0 to 15 of the 900 minus 375 leaves us with 525, and then minus 20q minus q squared dq. So an antiderivative is then 525q minus 10q squared minus 1/3 q cubed, which we are evaluating from 0 to 15. So evaluating at 15, we would have 525 times 15, which is 7875, minus 10 times 15 squared, so that's 10 times 225, which is 2250, minus 15 cubed divided by 3, which leaves us with 1125, or after simplifying, 4,500, measured in dollars here. All right. Now, the producer surplus is found by integrating over our interval from 0 to the equilibrium quantity, 15. The difference in the equilibrium price, which was 375, and we're subtracting our supply function, which was 10q plus q squared, integrating with respect to q. So we have, for our antiderivative, 375q minus the antiderivative of 10q would be 5q squared, and then minus the antiderivative of q squared is 1/3 q cubed, which is then being evaluated from 0 to 15. So when we evaluate at 15, we have 375 times 15, which is 5625, minus 5 times 15 squared, so 5 times 225, which is 1125, and then minus 15 cubed divided by 3, which is 1125. So we are left with $33.75 for the producer surplus.